In spherical geometry, we had this idea of excess, which is essentially how far my angle sum was away from 180. And that works in hyperbolic as well. So we're going to let S be the angle sum of a given polygon. So of P, where P is an n-sided polygon. Then our defect, which we denote by delta of P, is n minus 2 times 180. So what the sum should be in Euclidean space minus this sum that it is in hyperbolic space. So how far away we are from Euclidean. My first theorem about this, if we have that BDC in triangle ABC, so I have my triangle here with vertices ABC, and D is any point on this segment BC. And we're going to let delta 1 be the defect in triangle ABD. Delta 2 be the triangle or the defect in triangle ADC. Then adding up these defects gives me the defect of the larger triangle. So defects are additive, just like excess was additive. So let's label some of these angles and prove this. And this proof is going to be very similar to the way we did excess in spherical geometry. We know that the first defect is 180 minus the measure of angle 1 plus measure of angle 2 plus measure of angle 3. Delta 2 is going to be 180 minus the measure of angle 4 plus angle 5 plus angle 6. And then when I add these two up, delta 1 plus delta 2, 180 plus 180 is 360 minus angle 1 plus angle 2 plus angle 3 plus angle 4 plus angle 5 plus angle 6. Well, we know that this would be 360 minus the measure of angle 1 is the same as angle B. We have that 2 plus 6 is the measure of angle A. 5 is the measure of angle C. And then we have these two right here. Measure of angle 3 plus the measure of angle 4 is 180, since those are supplementary. Simplifying this gives me 180 minus the measure of angle A plus angle B plus angle C, which will be the defect of triangle ABC. So we have that defects are additive. Here I have a regular hexagon, a regular quadrilateral, and two isosceles triangles, and I want to find the defect of each of these shapes. I'm going to start with the hexagon. We know that it should be n minus 2 times 180. Since n is 6 for a hexagon, that would be 4 times 180, which is 720. However, we really have 6 angles, each which are 115 degrees each, which gives me 690. So the defect of my hexagon is 720 minus 690, or 30. Next, let's look at the quadrilateral. We know that quadrilaterals should be, once again, n minus 2 times 180, or 2 times 180, which is 360. However, in reality, we have 4 angles, each measuring 85 degrees, which gives me a total of 340. So the defect of my quadrilateral would be 360 minus 340, or 20. If I consider my triangles, this is going to be 180 minus my angle sum. We have two angles that are 5 degrees each. And then we need to consider this angle here. So a little bit of side work. We're going to look at the entire circle here and subtract out the parts that we don't need. So minus 115 and minus 85, which gives me 160. So I also have one angle that is 160. And so this would be 180 minus 170, or 10. So each one of these has defect 10. And I want to consider the defect of the entire hexagon. Just like before, we know that hexagons should be n minus 2 times 180, which would be 4 times 180, or 720. However, what we actually have, over here on the left, we have two angles that are 115 degrees each. My top and bottom angles are 115 plus an extra 5. And then my right angles would be 85 plus an extra 5. If we add all of these up, we get 650. So the actual defect of my outer hexagon will be 720 minus 650, which is 70. And once again, that comes from adding up all of the pieces. 30 plus 20 is 50, plus 10 is 60, plus 10 is 70. I'm now going to do my Aaa congruence. If we have two hyperbolic triangles that have the same angle measures, then they are congruent. And once again, this is going to follow my proof of spherical geometry very closely. So I have my two triangles ABC and XYZ. We're going to assume that all of their angles are congruent. And once again, we're going to suppose they're not congruent. This means that none of the sides can be congruent, since if they were, I would have angle side angle, which we know to be true. So let's assume ABC is the one with two longer sides. We're going to construct a point D on segment AB so that BD is congruent to XY, as well as a point E on BC such that BE is congruent to YZ. So essentially I'm going to cut out the smaller triangle from my larger triangle. Therefore, we have that this triangle and this one down here are congruent. I'm going to go ahead and draw the edge AE as well. And I'm going to label these defect 1, 2, and 3. We therefore have that defect 1 plus defect 2 plus defect 3 is going to be equal to the defect of triangle ABC by the additivity property, and this needs to be greater than the defect of 1, since I took defect 1 and added some extra stuff. However, defect 1 is also the defect of triangle XYZ, since it is congruent to the triangle with defect 1. They would need to have the same defect, which should also be the defect of triangle ABC, since we know XYZ and ABC have the same angle measures. And that gives me a contradiction, because I can't have this both greater than and equal to the same number. So therefore, these triangles had to be congruent to start with.